A cold stone sits on my porch, its weight steady under my hand. The night sky above feels like the cold of a cellar floor, each star a pinprick of faint light. I stare at a faint smudge of light that moves slower than the rest. That smudge is a galaxy, a whirl of stars that spins like a record on a turntable. When I first measured how fast the outer edges of that record turned, the speed surprised me. The stars at the edge moved far faster than the gravity of all the visible matter could pull. It felt like a wheel that kept spinning even after the axle was taken away. I find it hard to picture how a galaxy can stay together without an unseen hand. The first clue came from a man named Fritz Zwicky, who studied a cluster of galaxies in the 1930s. He saw that the galaxies rushed around each other far faster than the visible mass could hold. Zwicky called the missing pull dark matter, a term that has grown and shifted over the years. At first it was a guess, a placeholder for something we cannot see. Later, in the 1970s, Vera Rubin measured the rotation of many spiral galaxies. Her data showed a flat curve. The speed stayed constant far out from the bright core. If only the stars and gas we see were there, the speed should drop like a stone rolling uphill. Instead, the curve stayed level, like a treadmill that never slows. Ordinary matter, protons, neutrons, electrons, makes up only a few percent of the total gravity we feel. The rest must be something else, something that does not shine, does not absorb, does not interact with light. We call it dark not because it is evil, but because it hides from our eyes. The term has been refined. Some call it cold dark matter, implying it moves slowly compared to light. Others speak of non-baryonic matter, meaning it is not made of the atoms that build our world. No single word can capture all the ideas, and we keep adjusting the label as we learn. The evidence piled up. Gravitational lensing shows light bending more than visible mass predicts. Gas in clusters glows hot, yet the pressure needed to hold it together exceeds the mass we see. Even the cosmic background radiation bears tiny ripples that match a universe full of unseen mass. All these signs point to a hidden framework that scaffolds the large-scale pattern of the universe. I sometimes wonder if the hidden mass is a single particle, a sea of tiny objects, or something else entirely. We don't really know. Theories range from weakly interacting massive particles to axions to primordial black holes. Each idea brings its own math, each test pushes the limits of our instruments. Our telescopes listen for tiny flashes, our detectors sit deep underground, waiting for a whisper of a hit. Sometimes the silence is louder than any signal. It makes me think of a watch ticking in a dark room, each tick a reminder that time moves even when we cannot see the gears. If we follow the smallest halos, tiny clumps of dark matter that never formed many stars, we can trace how the big net of matter grew. These halos act like seeds, pulling gas together, shaping where galaxies can form. The pattern that emerges is a web of filaments and voids, a lace of matter that stretches across the sky. The web is not a smooth sheet. It is a rough, grainy mesh, like sand stuck between your shoes. Every filament is a line of dark matter, a rope that pulls galaxies into strings. Every void is a gap where the rope is thin, a cold pocket where few stars ever light up. Our story starts with those first clues, rotation curves and cluster speeds, and moves toward mapping that rope. We have built models that match the observed web, but the rope itself remains unseen. Some experiments claim a faint hint, a tiny bump in data that could be a particle. Others find nothing, and the mystery deepens. I admit I sometimes feel the weight of the unknown pressing on my thoughts, like a stone that never lifts. Yet the work continues, each new survey adding a grain of sand to the pile of data. Soon we may have a clearer picture of what makes up the hidden framework. Until then, the night sky stays cold, the stone stays heavy, and the galaxy spins on. A lone dwarf galaxy flickers, its stars barely warm. A tiny lens, a glass bead, sits on my desk tonight. It reminds me of the invisible lenses that bend starlight. Einstein first wrote that a mass could pull a ray of light. He imagined a star's gravity nudging a photon like a stone nudges water. The idea sounded odd, like a cold cellar whispering about heat. I find it hard to picture a mass actually touching light. Yet the math says the path curves, just as a watch spring bends under pressure. When the bend is strong, we see arcs and rings around distant galaxies. Those bright circles are called Einstein rings, a fitting tribute to his name. A perfect alignment makes a full circle, a slight tilt leaves a broken halo. Strong lensing also creates multiple copies of the same galaxy, like twin candles. Astronomers catalog these copies to measure how much hidden mass lies between us. The hidden mass is what we call dark matter, a cold, unseen sea of particles. We cannot see it directly, but we can feel its weight through light. Weak lensing works on a larger scale, where many tiny bends add up. Instead of a bright ring, we get a subtle stretch of many background galaxies. Statisticians compare the average stretch to a grid of invisible mass. The result is a map that looks like a grain of sand spread across a table. These maps reveal where dark matter piles up, like hills hidden beneath a field. One famous map shows the Bullet Cluster, where two galaxy groups have smashed together. The hot gas from the collision glows in X-rays, but the mass map shows a different center. That offset tells us the invisible mass passed through without slowing, just like a stone sliding on ice. It is one of the strongest arguments that dark matter does not behave like ordinary gas. To turn lensing data into a mass map, scientists invert the equations that link bend to weight. The inversion is a tricky math problem, like untangling a knot with a single thread. They must assume how the unseen mass is spread, then check if the predicted bends match what we see. If the match is good, the assumed distribution is likely close to reality. If not, they adjust the model and try again, a process that can take many nights. One source of error is the shape of the background galaxies themselves. We must guess their original shape, then measure how much it has been stretched. A wrong guess can make the mass map look like a hill where none exists. Another uncertainty comes from the distance to the lensing galaxy and the source galaxy. We estimate those distances from redshift, but the numbers carry a cold margin of error. Even a small slip can shift the inferred mass by a large amount. Instrumental noise also adds a grain of sand to every measurement. We smooth the data, but smoothing can erase real features as easily as it hides noise. Because of these limits, a single lensing map never tells the whole story. Scientists combine lensing with other clues, galaxy motions, X-ray maps, to build a fuller picture. Each method adds a weight, and together they balance the uncertainties. The result is a three-dimensional sketch of where dark matter lives in the nearby universe. It feels like feeling the cold of a cellar while holding a warm cup of tea. You notice the contrast, and the contrast tells you about the hidden walls. In the same way, lensing tells us where unseen walls of mass stand. I sometimes stare at a lensing image and wonder how a tiny photon knows its path. It doesn't make sense when you say it aloud. Light has no mind, yet it follows curves. The answer lies in the geometry of space, which bends like a stretched sheet under weight. Mass tells space how to bend. Space tells light how to travel. That simple rule carries the weight of galaxies, clusters, and the invisible scaffolding. When we map that scaffolding, we see patterns that hint at how the universe grew. The patterns are not perfect. They have gaps like missing stones in a road. Those gaps may hide new physics, or they may be the result of noisy data. We keep refining our tools, but we also keep the humility of a night watchman. The night watchman knows that some sounds are just wind, not a threat. Similarly, some lensing signals may be artifacts, not real mass. We cross-check with other data, like checking a compass against a known star. If the directions agree, confidence grows. If not, we return to the drawing board. The process is slow, like watching sand settle in a glass hourglass. Patience is the only tool that can read the faint signatures left by invisible mass. Every new lensing picture adds another grain to our mental pile of stone. Some grains are heavy, shifting our view dramatically. Others are light, barely moving the balance. I sometimes think of the universe as a vast, cold cellar, and lensing as the faint light through a crack. That crack shows us a sliver of the hidden architecture. The crack is narrow, and the light is fragile, but it carries weighty clues. When I look at the newest map, I see a faint line where a filament should be. It is thinner than a hair, yet it may hold a galaxy cluster together. I cannot be sure. The data are noisy and my eyes are tired. But the possibility lingers, like the scent of rain on dry stone. That scent reminds me that even the smallest hint can shift a whole theory. So we keep measuring, keep mapping, and keep questioning each faint bend. The night grows older, and the porch light flickers like a distant star. I glance at the glass bead again, seeing my own reflection warped by the room's shadows. It is a reminder that every curve we see may be a mirror of something unseen. A faint halo lingers around the distant galaxy, a thin ring of light. That ring seems to pulse, as if the mass behind it were breathing. I wonder if the breathing is real or just the flicker of my lamp. The lensing image does not answer, only offers a quiet clue. In the quiet, the weight of the unseen mass feels almost tangible. It sits there like a cold stone on the floor of my mind. I can almost hear it hum, a low tone like a distant engine. The hum fades as the night deepens, leaving only the ring's faint glow. I sit back, the porch swing creaking under my weight, and stare. The image stays, a small, cold reminder of the hidden world beyond. A single grain of sand sits in my shoe, stubborn and sharp. I stare at the night sky, the black above feeling as heavy as a stone. The porch light flickers, ticking like an old watch that refuses to stop. You asked about the network that holds galaxies together, and I will try to explain. Dark matter is invisible, but its gravity is real, like the pull of a magnet hidden beneath a table. It does not shine, it does not emit, yet it bends light and pulls gas. When the early universe was a hot soup, tiny ripples grew under its pull. Those ripples turned into thin streams of dark matter stretching across space. The streams are called filaments, long bridges linking clusters of galaxies. Imagine a cold cellar floor where dust gathers in long lines. Those lines are the filaments. Simulations such as Millennium and Illustris let us watch this process on a computer. In those models, billions of particles move under gravity, forming a web over billions of years. A single run can take months, the code humming like a distant engine. I find it hard to picture how a computer can hold a universe in its memory. The simulations start with a random field, then let gravity do its work. Dark matter collapses along the thinnest directions first, making sheets, then filaments, then knots. The knots are called nodes, where many filaments meet and massive clusters sit there. Observations from galaxy surveys like the Sloan Digital Sky Survey map the bright galaxies. Those maps reveal the same pattern. Long strings of galaxies with empty gaps between. The empty gaps are called voids, vast regions almost empty of matter. The filaments are the highways along which gas flows toward the nodes. Gas follows the dark matter, cooling, forming stars, building galaxies. A galaxy's life is tied to the filament it lives in, like a town on a road. Those in dense filaments grow faster, get more gas, become larger. Those in sparse filaments stay small, form fewer stars, evolve slowly. We see this in the colors of galaxies: red, dead ones in dense nodes, blue, active ones on the outskirts. The relationship is not simple. Many factors play a role, like supernova explosions and black hole winds. Open questions still linger about what dark matter is made of. It could be a particle we have not yet detected, or something more exotic. We have not caught a single particle in a lab, so we guess from its gravity. Some theories propose warm dark matter, lighter particles that move faster, smoothing out small structures. Others suggest cold dark matter, heavy particles that clump tightly, creating sharp filaments. We don't really know which picture matches reality. The simulations assume a type of particle, usually cold, and they reproduce the observed web well. But if the particle were different, the web might look a bit fuzzier. Future surveys, like the Euclid mission, will map fainter galaxies farther out. Those maps may show whether the filaments are as thin as we think. There is also the question of how much dark matter lives inside a filament. Measurements of gravitational lensing, how light bends around a filament, give us clues. The signal is weak, like hearing a whisper in a storm, and it takes many galaxies to see it. Some studies claim detection, others say the data is not strong enough. I sometimes feel the data is like trying to weigh a feather with a kitchen scale. The composition of filament dark matter could include small clumps called subhalos. Those subhalos might host dwarf galaxies, invisible unless we look very deep. If many subhalos exist, they could affect the motion of stars in nearby galaxies. Observations of stellar streams around the Milky Way show gaps that might be caused by such subhalos. That would be indirect proof that filaments contain many tiny clumps. The picture is still incomplete, and each new piece feels like a stone added to a wall. The wall is tall, and we stand at its base, feeling the cold air rise. Our models improve, but the underlying physics stays stubborn. Sometimes I think of the web as a set of ropes pulled tight by unseen hands. The ropes are not smooth. They have knots, frayed ends, places where they break. Those break points could be where dark matter decays if such a process exists. No experiment has shown decay, but the idea remains in some papers. Even if dark matter never changes, its distribution may shift as galaxies merge. Mergers pull filaments, stretch them, sometimes tear them apart. The process is slow, taking billions of years, like a glacier moving over stone. If we could watch a filament for a human lifetime, we would see almost nothing. That makes it hard to trust intuition. We rely on models and indirect clues. The Millennium simulation, run on a supercomputer in the early 2000s, still guides us. It showed that most mass ends up in a few massive nodes with filaments feeding them. Illustris added gas physics, showing how stars form inside the web. Both simulations agree on the large-scale shape but differ on small details. Those differences matter when we compare to real surveys. The weight of those differences feels like a stone in the pocket of a traveler. Sometimes I wonder if we are looking at the right thing at all. Perhaps the web is a side effect of something deeper, a property of space itself. We don't have a clear answer, and the silence of the night offers no comfort. Yet the night also gives a clear view. The Milky Way stretches across, a thin band. That band lies within a filament that connects us to the Virgo cluster. If you look up, you can trace the faint glow of that filament in the sky. It is a reminder that we sit on a thin thread stretched across a huge emptiness. The thread is cold, like the cellar floor beneath my feet, and yet it holds us. A single galaxy, our own, hangs from that thread, moving slowly toward the node. Its motion is measured by tiny shifts in the light of distant quasars. Those shifts are minuscule, like a watch hand moving a fraction of a second. When the data line up, they confirm the filament's pull. If they do not, we must rethink our picture. The search continues, quiet and patient, like listening for a distant clock. I hear the ticking in my mind, each tick a step toward understanding. A faint filament glows in a deep field image, a thin line of galaxies. It stretches across the picture, barely brighter than the background. That line is a piece of the web, a clue we can hold. I stare at it, feeling the weight of the stone I imagined earlier. The night grows colder, the porch light dimming, the stars unchanged. In this still moment, I notice a single, faint speck of light at the edge of the filament, barely resolved. A tiny knot of stars clinging to the thread. A cold stone sits on the porch rail, its weight steady against the night. I stare at it, feeling the same weight in the ideas about invisible halos. The first thing to know is that dark matter does not shine. It gathers in clumps that act like deep pits in a field. Those pits are called halos, and they come in many sizes. The number of halos at each size follows a simple curve. Small pits are many, big pits are few. That curve is called the halo mass function. When the mass function shifts, the count of galaxies shifts with it. More big halos mean more massive galaxies. Fewer small halos mean fewer dwarf galaxies. I find it hard to picture how a cloud of invisible particles can hold a galaxy. The answer is gravity, plain and relentless. Baryonic gas, ordinary atoms, falls into the halo pits. It speeds up, heats, and then must lose that heat to settle. Cooling is a slow sigh, like a watch ticking in a cellar. Radiation lets the gas shed energy, turning hot vapor into cold clouds. If the gas cannot cool fast enough, it stays puffed up and never forms stars. Cooling depends on the halo's depth and the gas's composition. Metal atoms act like tiny mirrors, scattering light and speeding cooling. Early halos, poor in metals, struggle more to lose heat. When enough gas cools, it collapses into a thin disk. There it fragments and stars begin to flicker. But stars are not quiet neighbors. When a massive star explodes, it sends shock waves through the gas. Those explosions are supernova feedback. They heat the surrounding gas, sometimes pushing it out of the halo. Active galactic nuclei, supermassive black holes, add another push. They launch jets and radiation that can sweep gas clean. Both supernovae and AGN feedback act like a sudden gust in a quiet night. They can halt star formation for long stretches. Observationally, we link galaxies to halos by measuring how they cluster. Galaxies that sit in massive halos tend to group more tightly. Weak lensing, tiny bends in background light, lets us map halo mass directly. It feels like feeling the weight of a stone through a thin sheet. Satellite counts around a central galaxy also betray the halo's size. More satellites usually mean a deeper pit. Yet matching these signs to computer models is tough. Simulations must track dark matter, gas, cooling, and feedback all at once. The biggest challenge is that feedback is messy. We cannot write a single equation that captures every explosion. Models often overproduce stars in small halos or underproduce them in large ones. Adjusting feedback strength feels like tightening a screw without seeing the gears. Resolution limits add another gap. A simulation that can see a grain of sand may miss the larger landscape. We don't really know if our recipes for cooling and feedback are right. Sometimes the numbers work, but the underlying physics feels forced. Observations of the early universe give us clues. The faint glow of distant dwarf galaxies shows that some small halos formed stars early. Other early galaxies shine bright, hinting that massive halos cooled quickly. These clues help us tune the models, but the fit is never perfect. It is like trying to match a broken watch to the ticking of a perfect one. Even with the best effort, simulations still leave a cold spot. The predicted number of tiny satellites around the Milky Way is far higher than we see. Some suggest that many satellites never formed stars at all. Others think they were stripped away by the Milky Way's gravity. Both ideas point to the delicate balance between cooling and feedback. When I look up at the sky from this porch, the night feels like a watch face. Each star is a tiny mark, each galaxy a larger tick. The dark pits of halos sit unseen, holding the weight of all that light. A single dwarf galaxy glows faintly, its light barely touching the stone. A faint speck on an old sky photograph catches my eye. It is a dwarf galaxy, barely brighter than a grain of sand stuck in a shoe. I stare at it as the night air grows cold, like the cellar beneath my porch. These tiny systems are dominated by dark matter. Their stars account for only a few % of the total mass. The rest is an invisible weight that holds them together. I find it hard to picture how something we cannot see can outweigh everything else. Because the stars are so few, the gravitational pull they feel comes almost entirely from the dark component. Their motions trace the shape of the hidden mass. A slow wobble of a star tells us the density at the galaxy's center. Here the core-cusp problem appears. Simulations that assume cold, dark matter predict a steep rise, a cusp in density toward the center. Observations of dwarf galaxies often show a flatter, core-like profile. The mismatch hints that our picture of the dark particle may be missing something. It doesn't quite make sense when you say it aloud, the idea that the simplest model fails in the smallest places. One possible fix is to give dark matter a tiny speed, making it warm rather than cold. Warm particles would smooth out the density, turning cusps into cores. The difference is subtle, like the ticking of an old watch compared to a newer one. Yet the effect shows up in the faintest dwarfs. Tidal stripping adds another layer. As a dwarf orbits a larger galaxy, the larger's gravity pulls away its outer stars and dark matter. Over time, the dwarf loses mass, becoming an ultra-faint relic. Some of the smallest known galaxies may be the stripped remnants of larger ancestors. These ultra-faint dwarfs are like the last embers of a fire that once burned brighter. Their stellar populations are ancient, formed when the universe was still a few 100 million years old. Because they have so few stars, any measurement of their motion carries large uncertainties. Still, the handful of stars we can track give a clear signal of a massive dark halo. Cold versus warm dark matter can be tested by counting how many dwarfs exist at different masses. Cold models predict many more tiny halos than we observe. Warm models suppress the formation of the smallest halos, bringing the count closer to reality. The discrepancy is a gap that researchers try to fill with deeper surveys. The upcoming legacy survey of space and time will push the limits. It will sweep the sky night after night, looking for faint, moving points of light. Its depth will reveal dwarfs that are currently invisible, like a stone hidden under a thin layer of dust. The data will let us compare the observed dwarf population with the predictions of different dark matter theories. Even with better data, some questions stay stubborn. How much of a dwarf's shape is set by its own dark matter, and how much by the tides of a bigger neighbor? I find it hard to picture the exact balance. The answer may lie in detailed simulations that include both gravity and the complex history of each system. If dark matter is warm, the smallest halos may never have formed. That would mean the ultra-faint dwarfs we see are the survivors of a cutoff in the mass spectrum. If it is cold, then many halos should be empty, lacking stars altogether. Those dark halos would be invisible, a hidden population we can only infer indirectly. The study of dwarfs also informs us about the early universe. Their stars carry the chemical fingerprints of the first supernovae. By measuring the metal content, we learn how the first generations of stars enriched the gas. The dark matter halo acted as a cradle, holding the gas together long enough for stars to form. In the end, dwarf galaxies are simple laboratories. They have few moving parts, yet they hold the weight of the biggest mysteries. Their faint glow reminds us that even the smallest lights can cast long shadows on our understanding. I sit here, the porch light flickering, and notice a single red star at the edge of the dwarf's outline. It twinkles, steady, a quiet reminder of the hidden mass that cradles it. A cold cup of tea sits on the porch railing, its steam rising like thin breath. I stare at the night sky, feeling the weight of a stone in my pocket. The oldest light we can catch is the afterglow of the big fire. Tiny hot spots in that glow tell us where invisible mass gathered. Those spots are not random, they match where dark stuff pulled on light. I find it hard to picture how empty space can tug on photons. When the universe cooled enough, atoms formed and light finally traveled free. That moment is called recombination, a name that feels oddly musical. At recombination, dark matter already formed a web of shallow valleys. Ordinary matter fell into those valleys, like sand slipping into a dent. The pattern of the afterglow acts like a map of that early web. Scientists read the map to count how much dark matter was present. The map's tiny ripples show the balance between light and heavy stuff. Around 100,000 years later, the universe's energy shifted. Radiation lost its grip, and matter began to dominate the stretch. That switch is called matter-radiation equality, a quiet turning point. After equality, gravity could grow clumps faster than before. Small clumps merged, making the first mini halos, barely larger than a city. These halos were made mostly of dark matter, invisible but massive. Ordinary gas gathered inside, cooling slowly like a cellar's damp air. The first stars, called population III, ignited within those dark cradles. Those stars burned hotter than any we see today, forging the first heavy atoms. Without dark matter's early pull, those stars would have taken much longer. I sometimes wonder how a particle we cannot see could shape such fire. Observations of the afterglow's unevenness give us clues about that pull. But the afterglow alone cannot tell the whole story of the first halos. A new tool, the 21-centimeter line, listens to neutral hydrogen's faint sigh. When the first stars lit up, they changed hydrogen's state, altering that sigh. By measuring the size strength across time, we glimpse when halos formed. Early measurements hint at a sudden dip, possibly the birth of the first stars. That dip matches models where dark matter helped gas collapse early. If dark matter were lighter, the dip would appear later, or not at all. Thus, the 21-centimeter signal acts like a quiet clock for dark matter. Current telescopes catch only a whisper of that clock, but it is growing. Future arrays will listen longer, hoping to hear the full tick. Each tick may confirm how much dark matter weighed in the early mix. The weight of that dark matter set the stage for everything we see now. Even the galaxies we admire owe their roots to those tiny early clumps. Without those clumps, stars like our sun might never have formed. I admit we do not really know the exact particle that makes the dark. We only know it does not shine, does not feel electricity and clumps. Laboratory searches try to catch a single grain, but the night sky still guides us. The afterglow, the 21-centimeter sigh, and the first stars together form a sparse puzzle. Each piece fits a little, leaving gaps we still feel in the dark. Sometimes I sit here, listening to the night insects, and think of that gap. The porch wood creaks, reminding me that even small sounds matter. In the end, the universe's first minutes were a cold, quiet scramble. Dark matter was the hidden hand, nudging gas into the first bright points. We watch the afterglow's spots, we listen to hydrogen's sigh, we wait. All of it feels like a stone rolling slowly down a long, dark hill. And as the wind brushes the porch, I notice a single moth hovering near the lamp. A cold bottle sits on the porch rail, sweating in the night air. The night feels as heavy as a stone dropped into a quiet well. I stare at the bottle and think about the invisible stuff that holds galaxies together. Dark matter is not a thing we can see, but it pulls on everything like a hidden hand. One idea that has long held a place in our thoughts is the weakly interacting massive particle, or WIMP. WIMPs would be heavy enough to slow down fast stars, yet they would hardly ever bump into ordinary matter. If a WIMP passed through a detector, it might nudge a nucleus just enough to make a tiny flash. Experiments deep underground try to catch that flash, but the signals are rare and faint. I find it hard to picture a particle that is both massive and shy. It doesn't make sense when you say it should be everywhere and yet never touch us. Another candidate comes from a puzzle in the laws of the strong force. The strong CP problem asks why a certain angle in the equation seems to be zero. The answer may be a new, ultra-light particle called the axion. Axions would be so light they could slip through the Earth without leaving a trace. If axions exist, they could turn into a tiny flash of light inside a strong magnetic field. Scientists point powerful magnets at dark rooms, hoping a faint glow will appear. Sterile neutrinos are a third idea, a cousin of the neutrinos we already know. Normal neutrinos are light and interact weakly. Sterile ones would not interact at all except through gravity. Because they are light, sterile neutrinos would move faster than heavier dark matter. That speed would make small galaxies form later, giving a slightly different pattern in the sky. Self-interacting dark matter offers a different twist. Instead of passing through each other, these particles could bounce off one another like billiard balls. If they do, the centers of galaxies might be less dense, matching some observations of dwarf galaxies. The idea changes how we picture the inner parts of galaxy clusters. Each of these candidates would leave its own imprint on the web of matter that stretches across the universe. WIMPs would create clumps that grow early, making dense cores in big clusters. Axions would behave more like a smooth fog, spreading evenly and only forming structures when gravity pulls hard enough. Sterile neutrinos would smooth out the smallest structures, erasing tiny clumps that would otherwise appear. Self-interacting particles would flatten the inner regions of galaxies, making them look less peaked. The way we test these ideas is to compare simulations with what telescopes actually see. We run a computer model, add one type of particle, and watch how the virtual universe grows. Then we look at real data. The way stars move in a dwarf galaxy, the way light bends around a cluster, the pattern of faint hydrogen clouds. If the model matches the data, the particle gains credibility. If not, we must look elsewhere. I sometimes wonder whether any of these ideas capture the truth. The night is quiet, and the ticking of the old wall clock seems louder than usual. The clock's tick feels like a reminder that time moves on, even while we chase shadows. Patience, WIMPs were once the favorite, but the lack of a clear signal has made many doubt them. Axions have gained interest because they also solve a different puzzle in particle physics. Sterile neutrinos sit at the edge of what we can see, offering a bridge between hot and cold dark matter. Self-interacting models are still new, and their effects are subtle, but they could explain why some galaxy cores look soft. All of these possibilities share a common thread. They would change how matter clumps together. The pattern of galaxies, the shape of clusters, the speed of stars, all would shift in measurable ways. When we map the sky with radio dishes, we see a faint glow that hints at the early universe. That glow carries the imprint of whatever dark matter was present at that time. If axions were abundant, the glow would be smoother, lacking the tiny ripples that heavy particles would make. If sterile neutrinos dominated, the ripples would be damped on the smallest scales. If self-interacting particles were common, the distribution of mass inside clusters would look rounder. Each clue is like a grain of sand stuck in a shoe. It hurts, but it also tells you where you've walked. The challenge is that the clues are tiny and the background noise is loud. Our detectors are like old watches trying to hear a single tick in a storm. We keep sharpening the tools, but we also keep reminding ourselves that we may be missing something entirely. Sometimes I think about the weight of a stone I once dropped into a pond. The splash was brief, but the ripples traveled far. Dark matter may be a stone dropped into the fabric of space, sending ripples we can only guess at. I don't have a final answer. Only a quiet porch, a cold bottle, and a sky full of stars that refuse to give up their secrets. The night air carries the faint scent of pine, and the bottle's condensation drips slowly onto the wood. A moth lands on the rail, pauses, then flies away into the dark. A cold metal lid rests on my porch table, weight like a small stone. I flip it open, hear the tick of a watch echoing from the cellar. Dark matter is the name we give to the missing weight that holds galaxies together. It does not shine, it does not push, it only pulls on stars. To catch it we dig deep, shielded from the chatter of the surface. Underground labs fill tanks with liquid xenon, a noble gas that glows when struck. Experiments like xenon and lux sit beneath miles of rock, listening for a single flash. So far they have reported only limits, numbers that shrink like sand through a shoe. Those limits tell us how often a dark particle could have nudged a xenon atom. I find it hard to picture a particle slipping through a crystal lattice. Some think the particle may weigh more than a grain of sand, others say lighter than a feather. If it is heavy, a tiny recoil may appear, a faint hint of motion. If it is light, it may glide through unnoticed, like a cold draft. Both possibilities push us to build larger, colder, quieter tanks. DARWIN will be a tank the size of a modest house, listening for fainter hints. It will run for years, hoping to hear the faintest tap from the unseen. We do not really know if that tap exists. Another route looks not for the particle itself but for what it might leave behind. When two dark particles meet, they could annihilate, turning mass into high-energy photons. Those photons appear as gamma rays, able to pierce the galaxy. Space telescopes scan the sky for such bursts, especially toward the galactic center. The Fermi satellite has found a glow that puzzles many researchers. Some argue pulsars cause the glow, others keep dark matter as a candidate. I cannot tell the difference without a chart in hand. Neutrinos offer a third messenger, tiny particles that slip through everything. IceCube, a cubic array buried in Antarctic ice, watches for sudden flashes of light. A dark matter annihilation could send a burst of neutrinos toward Earth. If IceCube catches one, it would be a clue, not a proof. Clues are like crumbs on a cold floor, scattered and fragile. The Earth's motion around the Sun should cause a tiny yearly change in detection rates. The DAMA experiment in Italy claims to see that modulation, rising in June, falling in December. Other detectors do not reproduce the effect, sparking a heated debate. I find the debate hard to follow, like listening to two clocks out of sync. Some suggest temperature changes in the detector material, not dark particles, cause the signal. Others argue the modulation is real, a direct hint of the unseen. The disagreement shows how fragile our methods are, like a thin glass. Gravitational wave observatories built to hear ripples of colliding black holes can also feel dark matter's pull. If a clump passes near the detector, it could alter the arm length ever so slightly. No such shift has been recorded yet, but the instruments grow ever more sensitive. Future runs may catch a faint hint of that effect. Axions present another candidate, particles that could turn into photons inside a strong magnet. Haloscopes place a magnet inside a copper cavity, listening for a tiny signal. The ADMX experiment reported a narrow line that could be an axion. Others say the line may be electronic noise, a glitch in the system. When the detector arms stretch and shrink as a mass passes, the change is measured in fractions of a millimeter, recorded by lasers that bounce back and forth, each pulse a tiny messenger of space and time. Quiet now. The search continues with new cavities, higher fields, colder temperatures. Each upgrade is a step toward hearing a softer tone. The tone may sit far below what our ears can hear, but the instruments can amplify. If that hope is wrong, the effort still teaches us about the universe. It teaches us how to build quieter labs, how to shield from background radiation. It teaches us how to count a single photon among billions. Those skills will help fields from medicine to geology. The detectors sit deep, like a cellar, cold and still. The xenon inside is kept at -180 degrees, colder than a winter night. The metal walls are thick as a stone wall, stopping most muons from above. A few muons still slip through, like tiny needles piercing the veil. When a muon passes, it creates a flash that must be ignored. Ignoring it is a skill, like learning to hear a single drum in a parade. We calibrate the detectors with known sources, then turn off the lights. The data streams in, a river of numbers, each a tiny heartbeat. Scientists sort the beats, looking for one that does not match the rhythm. A mismatched beat could be a dark particle or just a stray electron. Statistical methods help decide if the beat is real. They use confidence levels, usually 5 sigma, a high bar. 5 sigma means the chance of a fluke is about 1 in 3 million. That bar feels heavy, like lifting a stone with a single finger. Some argue the bar is too high for a field that is so new. Others say lowering the bar would flood us with false claims. I sit here, hearing night insects, thinking of those choices. The night air smells of damp leaves, a reminder of how small we are. The detectors far below are silent now, waiting for the next particle. If one arrives, it will leave a tiny mark, like a grain of sand on a scale. The scale will tip and we will record the shift. If no mark appears, we will tighten the limits, push the scale further. Each limit is a line drawn in sand, a boundary of our knowledge. The boundary moves slowly, as if pulled by a cold wind. A cold stone sits on the porch step, its weight steady under my hand. The night air smells of pine and old paint. I stare at the sky and think of the invisible mass that holds it together. We call it dark matter, though we cannot see it. It does not shine, does not glow, does not push on our eyes. It only shows its hand by tugging on stars. The first clue came from galaxies that spin faster than they should. A spiral arm glides past the center, as if a hidden hand pulls it. Newton's math says the outer stars should slow down. Instead, they race on, as if a stone were glued to a rope. Some scientists tried to change the math instead of adding hidden mass. They called it modified Newtonian dynamics, or MOND for short. MOND says the law of gravity bends when the pull is very weak. It replaces the missing stone with a new rule. I find it hard to picture a rule that bends only at the edge of a galaxy. The idea works for some galaxies, but not for all. Clusters of galaxies still need something extra, a weight we cannot see. So the community split, half holding dark matter, half holding MOND. A third group tried to mix ideas, adding new fields to Einstein's picture. They built tensor vector scalar theory, a mouthful that adds a vector field. The extra field acts like a thin sheet of invisible wind. It nudges stars just enough to keep the rotation smooth. The math is heavy, like a sack of sand in a shoe. Testing these ideas needs big telescopes and careful counting. We map how light bends around distant clusters, a technique called lensing. If dark matter sits there, the light should curve like a watch's hand. If MOND is right, the curve should look different, flatter. So far the curves match the hidden mass picture better. But the data are noisy, like the ticking of an old clock in the cellar. Some researchers built computer worlds where particles of dark matter clump. Those simulations form web-like structures that look like the real sky. The web is thick in places, thin in others, like a spider's net. If we replace the particles with MOND's rule, the net looks too smooth. That suggests the hidden particles do more than just add weight. Yet we have never caught a single particle in a lab. The Large Hadron Collider looked for them, but the detectors stayed quiet. We do not know if the particles are light, heavy, or something else. Some think dark matter could be a shadow of a deeper quantum world. Quantum gravity tries to join Einstein's smooth space with tiny, jittery particles. If dark matter is a glitch in that union, it might hint at new physics. A few theories propose that space itself has a grain, like sand in a shoe. Those grains could scatter light, making galaxies appear heavier. I admit I don't fully grasp how a grain of space could act like mass. Others suggest that dark matter is a field, a kind of invisible fluid. That fluid would flow through galaxies, pulling stars along. It would be similar to how air moves a kite, but far weaker. Testing a fluid requires measuring pressure in empty space, a hard task. Astronomers use the motion of dwarf galaxies to set limits. These tiny galaxies wobble less than expected if a fluid were present. So the fluid idea loses weight in those cases. Another line of work looks at how gravity works on the largest scales. If the law changes over billions of light years, the universe's expansion shifts. We watch distant supernovae to see if they dim as expected. The data show a slight acceleration, which we call dark energy. Some think dark matter and dark energy could be two sides of the same coin. If a single field does both jobs, it would simplify the picture. But the math grows tangled, like a knot in a rope. We have built surveys that count galaxies across the sky. These surveys map where mass gathers, visible or hidden. The patterns match predictions that include dark matter particles. If we remove those particles, the patterns fall apart. Still, a few outliers linger, like a lone rock on a smooth road. Those outliers keep the debate alive as long as we keep looking. One experiment tries to catch a dark particle by listening for a tiny flash. The flash would be a whisper of light, barely above the cellar's cold. So far the detectors hear only silence. Perhaps the particles are lighter than we thought, slipping through the net. Or perhaps they interact only through gravity, making them invisible to all other tools. If gravity is the only link, then dark matter may be a feature of space itself. That brings us back to the idea that Einstein's equations might need a tweak. A tweak could be as small as a missing term, as large as a new field. We have not yet measured that term directly, only inferred it from galaxy spins. The next generation of telescopes will watch the sky with sharper eyes. They will count the motions of billions of stars, like counting grains of sand. If the motions line up with dark particles, the case strengthens. If they line up with a changed law, the case for MOND grows. Either way, the night will keep its quiet, the stars will keep their spin. We do not really know which path the universe chose. I sit here, the porch light flickering, feeling the weight of a stone in my pocket. The cold wind brushes my cheek, reminding me that some things stay hidden. A moth lands on the light, its wings trembling like a watch's second hand. I watch it pause, then lift, as if questioning the very air it moves through. A tiny grain of sand sits on the porch rail, unnoticed by most. It feels like the weight of a stone pressed into my palm, steady and cold. I stare at the night sky, the ticking of an old watch echoing in my head. Dark matter still hides, like a cold cellar where no light reaches. Next-generation surveys are about to open new windows. Euclid will map billions of galaxies, tracing invisible gravity with fine detail. The Rubin Observatory will sweep the sky night after night, catching faint flashes. These projects mix astronomy and particle work like two old friends sharing a drink. Physicists bring knowledge of tiny particles. Astronomers bring maps of huge structures. I find it hard to picture how a single particle could shape a galaxy cluster. We don't really know if the same thing that makes a proton heavy also pulls stars together. Machine learning tools will scan the massive maps for patterns we might miss. Algorithms will learn what a dark matter filament looks like, then flag odd spots. The code will act like a diligent clerk, sorting through endless rows of data. Some people worry that a computer cannot replace a human eye. I think the opposite. The computer can flag the subtle, the human can judge the odd. If a direct detection finally arrives, cosmology will change in a quiet way. It would confirm that the invisible mass we infer from galaxies is real. Models of the early universe would gain a firm footing, no longer floating on guesses. A confirmed particle would also force us to rewrite textbooks. Students would learn that the universe is not only made of atoms, but also of something else. Philosophically, seeing the unseen feels like hearing a whisper in a stone wall. It reminds us that nature keeps secrets, even when we think we have all the answers. The future horizon feels like a long road under a heavy sky, each step measured. We will watch new data pour in like rain on a tin roof, steady, relentless. There will be false alarms like fireflies that die before we can catch them. We must keep a steady hand, not rush to celebrate every flicker. Collaboration will grow, with labs sharing detectors and telescopes sharing schedules. Funding will shift, some money moving from particle accelerators to sky surveys. I sometimes wonder if the answer lies in a single, tiny particle or in many. Maybe dark matter is a family, not a lone wanderer. Theories will keep shifting, like sand slipping through fingers. Some will propose new forces, others new dimensions, each trying to fit the data. Machine learning will help test these ideas, comparing predictions to maps. It will be a quiet judge, measuring error, pointing out mismatches. What matters most is the willingness to change our view when evidence demands. Science thrives on that humility, not on stubborn pride. Even if we never catch a dark matter particle, the maps themselves are a gift. They will show how matter clumps, how gravity sculpts the cosmos. I admit I sometimes feel the weight of the unknown pressing on my shoulders. It does not vanish with each new telescope, but it does feel a bit lighter. The night air grows colder as I sit, the porch lamp flickering. A single distant galaxy glows, a tiny point of light unchanged.